Okay, chemistry time. Chemistry time set up to annoy some people. Today's annoyance comes to you in the form of, we're talking about thermochemistry. This won't take very long, partially because I'm not going to get into a lot of detail. I would like to just show you some of the math that I would like for you to be able to do for this, and some of the very broad concepts, including, hopefully, some examples. So the objective for this talk on thermochemistry is, I can't read it, would you please read it to me? Okay, determine thermochemistry quantities. Determine thermochemistry I'm trying to figure out where I should put my quantities using lab, I'm just going to abbreviate that word, models. Okay, so in fact, you'll recognize from the nature of the objective, you've actually already met the objective, because the objective is about how this is done in the lab. And so why don't we start by you telling me about thermochemistry based on what your lab showed you. Can't figure out what. Yes, okay. So a chemical reaction, in the case of your lab, the chemical reaction looked kind of like this, right? I mean, this was the setup. The chemical reaction didn't look like this. But you had a very basic, we could call this a kind of, oops, I've already spelled it wrong. Calorimeter. That's a word you should probably know. A calorimeter, the suffix meter means it's going to measure something. And can you guess what it'll measure? Calories, which is a unit of thermochemistry. It's a unit of thermal energy. So this is based on the calorie, which is a unit for thermal energy, relating to, of course, thermal chemistry. The chemistry, the way that particles combine and recombine, is chemistry, and we're talking specifically about how that can generate or absorb heat, how that relates to the manifestation of heat in the physical universe. And so in your lab, you had, the actual part of the lab that was the reaction was, you had this chip. Now, the chip was not sugar. You know, it probably had some sugars in it, but basically, as this chemical reaction occurred, the chip would have gone through various stages of breaking down from starches, which are a ring of 3 sugars, into sugars, and then that would burn. And so basically, the chemical equation that we could write is C6H12O6, the formula for sugar, combined with what? What did that, this is once again starch, which would have a similar chemical formula, although not the same, but starch in the chip, and oils, which I'm not going to worry about right here, but they would be made of something like fatty acids. But we're going to focus on the starch because it'll be easier. So the starch combined with what? Yeah, when we were, well, you tell me in layman's terms or in elementary school terms, what did you do with this chip? Burnt it, right? You had a little fire down here. Okay, so you burnt the chip, and burning is a fuel, in this case a starch, combining with what? That we often don't even think about because we're so used to being in it. Air. So combined with oxygen from the air to form what? Do you remember what do combustion reactions? This is a kind of combustion reaction. Yep. Okay, so definitely it did, and that's actually the point. That's where we're getting. It did produce heat. We don't always indicate that in a chemical reaction, which is why I've drawn it in red, also because hot. But what chemical products did it create? You'll remember from your lab that the ash that was left over had less mass than this. So where did that mass go? 2 things. Nope. The ash had some mass. Let's say we had 10 grams of this. You might have gotten 1 gram of ash. Where'd the other 9 grams go? Yeah, in the atmosphere as what? Combustion reactions always produce, carbon dioxide and what other? What else is left? If we eliminate the carbon, some of the oxygens, we're left with what? Water. Water, good. So this is not all thermochemistry is combustion reactions, But combustion reactions are always involve thermochemistry because by definition they produce heat and light. So a combustion reaction is a kind of thermochemistry reaction because it deals with the heat of a chemical reaction. It generates heat. And then in our setup, we also had some water up here. And what happened to that water? This is what we measured. So the independent variable was the different kinds of chip, right? Because you did, the Takis basically? Or did you, what were they? Yeah. Dinamitas, right? Yeah. You did the dinamitas. And so the independent variable was you did the dinamitas, another group did Funyun flavored Lay's, another group did honey mustard flavored Lay's. Other brands are available. Lay's is not a sponsor of this video. But you each did a different kind of chip, and your dependent variable, what you measured was, how much the temperature changed. And not just the temperature itself. You had to measure it before and after because we were dealing with delta T. Okay? So that's one quantity in thermochemistry. It's delta T. Delta capital T is change in chemistry. Another quantity is thermal energy, which we abbreviate Q. Now, let's see if we can give the other two. There are two other quantities that change in the basic method of thermochemistry, calorimetry. The basic method of thermochemistry changes under two other conditions. How else? If we used different sizes of chip, which you did you get different changes in temperature? So what else does that tell us matters about this equation? Yeah, not just size, but specifically the quantity, the amount of matter in it, which we call, not the volume, mass. There you go, the mass. Okay, and this one will be a little bit trickier, but I'll just tell you, the kind of fluid that we're warming up makes a difference too. And so if we use something other than water, it would have changed temperature faster or slower, and that's called C, which is specific heat, which you should remember from your vocab. Specific heat is basically how, if a given amount of energy is added to a substance, how much it changes temperature. Low specific heat means it changes temperature fast with very little energy, which we usually say is a good thermal conductor. And then high specific heat takes a lot of energy to change a very little bit of temperature, and that's called a good thermal insulator. So a conductor has a low specific heat, an insulator has a high specific heat, in the most basic way. Insulator. So a thermal conductor conducts heat well. Let me give you a kind of usual example for that. I have a little setup here that even though you don't use it, Tatum, you see that I use it almost every day. And I have here a good thermal insulator. Why? Why would I want to, assuming this is hot, right now it's empty, but assuming this had hot tea in it, why would I want this to be a thermal insulator? Yeah, to keep it from both losing heat into my desk, which would both heat up my desk, which might damage the wood, and to keep it from cooling down so fast. And now why might I want this to be a good thermal conductor? Yeah, I do put it on, sometimes I put it on a hot plate, and I want it to absorb heat from the hot plate faster. So we use thermal, it's not like insulators are bad and conductors are good, it's that we have different uses for both of them. And so we take these quantities, specific heat, basically how much it is a conductor or an insulator, mass, how much stuff there is doing this chemical reaction, how much the temperature changes, and we can find from that how much thermal energy was either released or absorbed. And we use the equation, we put all those together in this equation, let me do a different color here, blue, Q equals MC delta T. I like to have them in this order. I think your book uses CM delta T, but the way that people remember this a lot of times is I just tell them Q equals M cat. This is not an A. This is the Greek letter delta. But if you remember that it looks kind of like the word cat in English, maybe that'll help you remember it. It's kind of silly, but so again, Q is thermal energy, M is mass, C is specific heat, and delta T is change in temperature. The most usual way for us to measure these things is that Q is in what? What unit do you think we use for thermal energy? Remember from physics probably. Joules, yeah, good. Very good. Joules. M is in the SI, M is almost always. Yeah, kilograms usually. I mean, we can definitely do it in grams. C is specific heat in joules per kilogram Kelvin, and then delta T is change in temperature. That's very important. It has to be change in temperature, and that's measured in Kelvin. It can be degrees Celsius. You just have to be careful. If you're given C in joules per kilogram Kelvin, make sure your delta T is in kelvins. If you're given C in joules per kilogram degrees Celsius, make sure delta T is in degrees Celsius. Basically, the units have to work. Furthermore, in the same way, if it's given in kilograms, make sure that your C is in joules per kilogram Kelvin, and if it's given in grams, you either have to convert or make sure your C is in joules per gram Kelvin. All of those are options. Like it's not like it's always in kilogram. We often also use grams. This is sometimes given in joules per gram degree Celsius, and this is very frequently, in fact, probably more often measured in degrees Celsius. But the nice thing about delta T being change in temp is that kelvins and Celsius would be the same change in temp, and so that shouldn't matter. Remember, we just add 273 to get to Kelvin. Do you have questions about how we might use, this is the calorimetry equation, Q equals MC delta T, which is I shouldn't say easiest, but it's the most fundamental part of thermochemistry. Do you have questions about how we might use this? So you would be given something like, such and such is the specific heat, it changed this much temperature, it had this much mass, how much heat was produced or how much heat was absorbed, and then you just plug and chug, as we say. So that's calorimetry. The next part is a little bit more, I guess, interesting, in my opinion, interesting and involved, which is the calculation of enthalpy. So enthalpy, I'm going to erase this top part. Is that okay if I erase this diagram? Probably enthalpy and entropy are together what we'll talk about for the rest of this. And they're a little bit, they're more complicated to understand, in my opinion, than what we just talked about with the calorimetry. But we're talking now about enthalpy. Whoops, let me try to spell it right. Enthalpy. So enthalpy we abbreviate as delta H. And enthalpy is basically how much heat energy a system has. Let me say that different. How the heat energy of a system changes. And we always, every single time talk about delta H. We never talk about just H itself. There's actually no way to measure enthalpy. We measure change in enthalpy, how much heat it has, or how much it has gained, or how much it has lost, not just how much it contains, because that's immeasurable. So we do this for chemical reactions. So we would have delta H for any given reaction is equal to the final delta H minus the initial, I should probably just use F, minus initial delta H, or delta H sub naught. You'll remember this kind of notation from physics, Tatum, where we used F for final and 0 sub naught for initial. Another way we sometimes express this is delta H of the reaction is equal to delta H of the products minus delta H of the reactants. And you can see those relate to initial and final. We initially had reactants, and finally we have products, and so these two things are both used to calculate enthalpy. And so if you're just given enthalpies, you can calculate that change. And this is important for Q also. Negative delta H is exothermic. That's also true for Q. In the most customary way, Q is expressed as negative if it's exothermic. A lot of times, though, I will say when we do these, you'll say just straight up how much energy was lost. And so that's exothermic automatically without putting a negative. But in this one, we use negative to mean an exothermic reaction for delta H. And to do delta H calculations, we just straight up subtract them. So you might have, it might say, let me give you an example from the book. The reactants have a delta H, the delta H of the reaction is negative 1,625 kilojoules, and the reaction of iron plus oxygen yields iron 3 oxide. And so the delta H of the reaction is negative 1625 kilojoules. We just added those together, and that means it's an exothermic reaction. Your book goes on to talk about how exothermic and endothermic reactions are used by human beings, but you can, well, how would we use an exothermic? What would be a good use for an exothermic chemical reaction? One that produces heat. Yeah, okay, there you go, a stove. You could cook food on it. Keep your house warm, like there's lots of them. What would be a good use for an endothermic reaction? Well, endothermic, so it's absorbing thermos, heat. So it would feel cold. When would we want something to be cold? Air conditioning, there you go. Air conditioning is, it's not that itself, air conditioning and refrigeration are not just chemical processes. They're not a chemical reaction causing an endothermic, well, it's not an endothermic reaction. It's more about pressure changing, or at least it's partially about pressure changing, but you're right. If we had an endothermic reaction, we could use that for refrigeration. Next. Yeah, again, we can, if you're given the thermochemical equation for some reaction, you can just add the products subtract the reactants from the products, and that's how you find delta H for the reaction. So if you're given, the delta H of the products and the reactants, you just do that simple math to find them. That one doesn't come up very often because much more often we use this. Do you mind if I erase this bottom part? We use this person Hess's law. This is probably where the bulk of your mathematical force will be brought to bear. So Hess's law. I said before that we've already done the objective. We've already determined thermochemical quantities in the lab. But this is the main mathematical model for thermochemistry, is Hess's law. And Hess's law states, I want to say it right, if you can add two or more thermochemical equations to produce a final equation, then the sum of the enthalpy changes for the individual reactions is the enthalpy change for the final reaction. So, for instance, it wants us to find, I'm just going to use this example right out of the book. It has this one. I wish I was doing it in a different color. Can you see on the screen if that's even visible, the brown part where it says Hess's law? 2s plus, 3O2 yields 2SO3. And it wants us to find delta H. So we want to find the delta H for this reaction, and we are given these other quantities. I'll just put given. There we go. Given S plus O2 yields SO2. And for this one, delta H equals negative 297 kilojoules. Hey, by the way, if it's negative, what kind of reaction is this? Exothermic, good. And we're also given that SO3 yields 2SO2 plus O2. Well, that doesn't add up, does it? Oh, 2SO3, sorry, yields 2SO2 plus O2. And for this one, delta H equals 198 kilojoules. So these are the things we would be given. So all of this came from the book, basically. We want to find the delta H for this equation. And you can see, you have to think about it in terms of reactants and products. So in this one, sulfur is it's a reactant. It's a reactant. And in this one, sulfur is a reactant. Good. In this one, oxygen is a reactant. But in this one, oxygen is a product. And so if we were dealing with the oxygen, we want to flip that. Anytime that we have a reactant and we want it to be a product, we flip it. This SO3, for instance, is a product, but here it's a reactant. And so this equation, we just said the oxygen we wish was a reactant, right? Boop, 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 boop. And the SO3 we wish was a product. And so we're going to flip this. And by doing that, can you guess what mathematically it does to this? Yeah, exactly right. That's it. If we flip it, if we want the products to be reactants and vice versa, we just change the sign on it. And then all we have to do is if the numbers don't match, like for instance, here's 2s in our equation we want to find, but here it's just 1. And so we want to double this one. So this one we want to double. And these are really our only two options. For these given equations, we will either multiply them or flip them, sometimes both. So we're going to double this. So our delta H for our reaction is going to equal 2 times negative 297 kilojoules. Do you see why? Why 2 times negative 297 kilojoules? Yep, because we needed 2 sulfurs, but we've only got 1. And then minus, I believe. Yeah, minus. Well, we had to flip this one, so... Oh, actually, sorry, we're going to add them. So plus minus, that's what it is, 198. Do you see why it's minus 198 now? It was plus 198, or it was positive 198, and now it's negative because we had to flip it. And so for our reaction, delta H of the reaction equals, well, 2 times negative 297 is negative 594. So negative 594 plus negative 198 would be negative 803? Negative 800 and, no. 594, let's see, negative 600 minus 200 would be negative 800. So it's going to be 790, negative 792 kilojoules, I believe. So the answer, what was the delta H for this reaction? We use these other 2 reactions and their delta H's, which we were given. We manipulate them a little bit, add them together. That's Hess's law, by the way. And we end up with the total change in enthalpy for our reaction, our given reaction. So basically Hess's law is change in enthalpy of a given reaction is equal to change of enthalpy for reaction A plus change of enthalpy for reaction B, etc. We add as many together as we need to. And conveniently for this, very conveniently, you have an appendix at the back of the book on page, this will be the last thing, page R, on page 975, reference table R11 is a heat of formation value given in kilojoules per mole. And basically, these are for individual substances from their constituent substances. Is given in kilojoules per mole. So you look up a substance and it'll tell you, for instance, if you had water, what you're basically looking up is H2O, or sorry, H2 plus O2 yields 2H2O. 2H2 plus O2 yields 2H2O. So if you look up the enthalpy of formation, this is to form 1 mole of water. The molar enthalpy of formation for water is negative 285.8. Negative 285.8 kilojoules per mole. So the table only says this part. But what it basically means is this. From its constituent elements, it takes this much energy to form this substance, or rather, in this case, it gives off that much energy. So in the same way, we might have been able to just look this up on table R11 on page 97. We just look up this product, and it will tell us this, and that implies from its constituent elements. Yep. And the reason it's molar is because this is for if everything in this case 1 mole. But guess what? We needed 2 for our thing, and so we doubled it. And so you basically use this table, you could look it up online, but for instance this table, to find molar enthalpies of formation. Use those as the equation, and then use that to find your enthalpy for your final equation. I really like Hess's law of problems because people have a difficult time with them. And when I say that, I mean I have a difficult time with them when I was learning them, because they kind of are like not in the strictest sense just math. They're kind of logic too. Like you have to be able to organize things in your mind, and you eventually get better at that, which makes you a better person because you can organize things better. So it's kind of like, it's a little bit more than math. It's math plus organizational thinking. I'm sure there is a way you could set this up with a table to keep it all straight, but for me, just keeping it straight that I have to double this one and flip this one makes it so my mind works better on that. But so that's the math for this chapter. The Q equals mc delta T shouldn't be too hard, and that describes thermochemistry at its most basic. And then Hess's law, and to a lesser extent enthalpy in general, are where we will find most of our actual math difficulties for this topic. Yeah, absolutely. Great question. One way you can tell is that the Q from Q equals mc delta T was measured in joules. It can be. It can be calories. I should have said that earlier. Calories and joules both measure energy. And then this is measured in joules too. And so they absolutely work together. You conceivably, I don't think there are any questions like this in your book, but conceivably you could find one of these, have its enthalpy, and then use that as a Q in another problem to find its specific heat, for instance. You won't have to do that, but do you have other questions? Thank you for that one.